Hello everyone, I welcome you to the day 25 of the training. Today we are going to implement another project in terms of FIFO design, that is one kind of buffer implementation at the IO buffers. FIFO is nothing but first in, first out of the IO buffer protocol, or it's kind of a memory design which resembles the memory design, but it is just a transition phase where temporarily the data which comes in first and the data which should go out first, that is decided in this entire structure, and this is the most essential element at the buffer stage, at the input output buffer stage. And we will see how to design it and how to verify it. And this is a bit lengthy topic, and this project is done in phases. Please stay along and please be consistent, and I welcome you to the day 25 of the training. So without any delay, let us go to the today's agenda. What is FIFO and what it is used for, and why do we need a FIFO implementation in the design after the entire bigger architecture? What is the major key point of FIFO implementation, and examples of FIFO as well. Usually not much examples. We have a single clock domain of the single clock design of a FIFO, and later we will discuss about the actual implementation of the FIFO project as well. So think of this is an introduction to the project. So project will be discussed in the later session of the trainings. Let us go to the topic. What is FIFO? Between two modules or any other peripherals, if you have considered this FPGA and some external, some RAM, and if you want to communicate this FPGA functionality with this RAM and send data, the data will be going in a flow, right? That flow of the data will be going with a piece of hardware that is nothing but FIFO. So in the FIFO, we have a key element called as the pointers. So based on the pointers, from which pointer we should collect the data, that is selected, and that take the form of binary counters. So I'll explain this in a bit, but understand FIFO has pointers inside it to point out the data that should come out first, and the data that comes in first, that is to be pointed again. Okay, this data has come at this point of time. So kind of pointers. So those can be represented with binary counters. The counters are responsible elements for generating the address locations internally, so there will be no external address signal located. Usually in the memory designs, we do include the memory location by user interface, or we will manually decide what memory location we need to access for the data. If you are reading from the memory, we should specify, we should mention the address location, or if we are writing onto the memory, we should mention from which location of the memory we are writing the data. So in the same way, if you have two modules and between these modules the data is sent in a particular protocol manners, and that is nothing but one piece of hardware, that is FIFO, first in first out. So for that first in first out, how is the data transmitted in a first in first out manner? I'll be explaining in a little bit, but see, this is a clock 2 and clock 1. You have two clocks at two different clocks. One is operating at 50 megahertz and another one is operating at 100 megahertz. How do you transmit the data between two different clocks? There should be some bridging gap between two different clocks, right? So that can be managed by the FIFO buffer as well. So there are many advantages in sending the data between two modules and operating the data between two modules at different clocks. That is the advantage. We will discuss it in the next coming slides. as this process of address pointing is automated. So how it is automated? The internal counter kind of structure will generate some addresses. You will understand the FIFO architecture better in the next coming slides. Let us go to the components of FIFO. As we have discussed just now, for a FIFO, okay, good, you are connecting these two modules with a IO buffer called FIFO. But inside IO buffer, if you have seen this FIFO, what are the components inside FIFO? How this FIFO design, how this black box is now operated? What are the internal components? Like just recollect a memory of FSM. In the finite state machine, how this finite state machine is implemented? What is the architecture? We have next state block, memory block, and output block. In the same way, for this FIFO architecture, FIFO implementation of the hardware, we have certain blocks inside the FIFO piece of hardware. See, think of this as a hardware device connected between two modules. Okay, like think of this as a USB cable, like a hardware in the external peripheral, but this is not USB cable. But even in the data cable, if that has a series of layers of electronics in it, if they that has, let us consider an Apple C to C cable, it has a bunch of electronic cables at the both ends of the type C. Hence the data processing is happening fast and even the charging is happening fast. That layers of electronics will do the part. How do they do that? They do that with a particular protocol. That protocol kind of structure is way more similar to this FIFO implementation between any modules or between the architecture of the FPGA and the external peripherals. So it is similar. As the process of address pointing is automated, that is what, for particular point of address in the FIFO location, whatever the data is transmitted, that point of data is stored and that can be sent after some series of data transmissions to the output thing. So let us go to the components. What are the internal components? We have a RAM. We should have a memory, like temporary memory. Let us consider a temporary memory in the FIFO. And also we have an up down counter. Very good. You have an up down counter. I am mentioning as UNDC counter, and flag logic. Flag logic is nothing but it is a state of functionality. Like for example, if some task is done, what is the output obtained? Whether this FIFO is working or not, whether this entire memory is full or empty, that you will get to know. Just understand some logic, some acknowledgement. Flag is nothing but acknowledgement. Okay, it is telling something to us. It should tell something to us, or else we will be unknown. See, all these hardware pieces won't talk to us, but they can indicate something. For example, in any circuit, if you are transmitting data, or if in a digital communication device at the receiving end, if you are collecting the data bits at the digital data bits after the Hamming code and the reception with no errors, if you have collected the signal and then if you have attached some LED circuit for blinking, that is an indication. That kind of acknowledgement is must and should required for every hardware that we write. So for that, see, till now memory signals have read and write command signals. So these signals are given by us, but here the FIFO should give some signals to us, like some flag, some acknowledgement. Flag is nothing but acknowledgement. Think of that way. What acknowledgement it is giving, I'll let you know these conditions. And also some static memory. Some static memory is nothing but some status logic. Some logic also indicates the counter address locations. So let us go to the architecture development. Now you are seeing this is the architecture. The address locations are generated by the counters in terms of read pointer and write pointer. We call them tail and head, or else read pointer and write pointer simultaneously, and for separate read and write operations respectively. So like, now understand, FIFO is a piece of hardware at some buffer, output buffer. In the previous lecture you have seen the IO buffer cells, right? In the buffer cells, some buffer cells have FIFO. If we design that, buffer cells can be turned into FIFO design, and that FIFO design have a architecture like one write counter, read counter, and also static memory called some status logic. Address is equal to 0 in the initial condition, and flag logic. What is full and empty? Full and empty is nothing but in the RAM, listen carefully, in the RAM, if you have these all registers, let us say you have 8 arrays of registers, 8 registers, arrays, 8 arrays, and in each array you have 8 bits of data, 8 bits of data, it is representing C9. So 8 bits of data, and for these 8 registers, if 8 registers have all the data full from the data in, and for example you have been giving the data from memory module to the another display module, let us say, to the output, but before going to the display module you have a FIFO connected. So what it should do when the data is coming to this RAM, so we are writing data to this RAM, right? So hence we have a counter called write counter. Why? Because here the address location will be written. In the initial the address is 0, so 0, and data is written. For the next address location to the increment of 1, see, every address location is incremented by 1. Like this it is incremented by 1 and it reaches to the 8th register, and at the data output whatever the register value is there, that is sent out here for first iteration. In the second iteration, let us see with another color, whatever the, okay, I have took the wrong color. Whatever the data in the 110, that comes to the 11 now, because in the 111 last register the data is already sent there and now it is empty, and 110 is coming here and some other data is pushed forward to the first one. So in this way all the registers are having data, full data in all the registers, then full, it says full. The logic acknowledgement says okay, FIFO is full, RAM is full, the RAM inside the FIFO is full. Or else let us consider the initial condition, everything is 0 0 0, all everything is entire 0, there is no data, there is no information, then empty is 1, full is 0. Full is 0 means there is nothing to be read from, like full is, it is not full. And if full is not equal, if full is not equal to 1, I mean full is equal to 0, that doesn't mean there is no data left in it. There might be some data. For example, in the 8 registers, if you have one register of data and all 7 are empty, then full will be 0, but empty will also be 0. That is another condition. So this kind of representation, by this representation, and it means an acknowledgement to us to understand, okay, this is the structure that RAM is letting us know that all the data is full or no data is there, it is complete empty, or some data might be there, so such that full is not 1 and empty is also not 1, right? So that is how FIFO works. These are all the components, and this counter is responsible for generating the address values. And why do we have read counter separate and write counter separate? We will get to know in the next coming slides. Let us see. Now we have static memory. What is static memory doing here? Static memory is used to initialize the counters. For example, in the initial state, counter is 0. And these are the inputs and outputs. I'll explain. But understand, static memory is used to initialize the counters. That is nothing but address generating modules. This counter is nothing but address generation. Address generation. This is address generation. Read counter. Okay. The status flag logics and the status flag logics are also understood from the static memory. Right? If static memory reaches to 7, the counter reaches to 7, write counter reaches to 7, static logic will be full. That entire thing is full and it says full is equal to 1. In the same way, if static memory address tends to 0 again, it comes to the ending point from highest to lowest. In this way, the empty will be 1. Okay, initially static will be 0 and then logic turns from full to 0 or 1, empty 1 to 0. Okay, and now let us understand one by one what are the input output pins and what is the data transmitted here. And we have data input bus. That bus is nothing but 8-bit bus, 8-bit wire data in, and output data out, buff out, that is 8-bit. And here we have write enable and read enable. These are connected to the RAM. See, memory designs we have done till the last 3 sessions or 2 sessions. We have done memory designs. For that we are writing read signal and write signal. So hence here I have named it write underscore n, but earlier I have named it mem underscore read or mem underscore write. Got it? So in this way I'm writing the commands in the memory design, but now these are same functionality. These have the same functionality and those will be utilized in the same manner for read and write commands. If read enable is 1, the entire information from the RAM is coming out to the data output. In this way, follow the green line and follow the red line here. And yeah, and another thing is write clock and read clock for different clocks, because at some particular amount of time write can happen in the FIFO, because write has a separate direction and read has a separate direction. You will get to know in the later stages of this thing, but as of now, in the from the beginning you have understood what FIFO is doing, what is the implementation usage of this FIFO, and then what are the components of it. And now let us talk about the components architecture inside the FIFO and what is each module responsible for, and then now how they are connected. For example, you have a data at this write clock and this D is sent through the static memory logic, and then when static memory logic address is initialized at 0, that address location in this write control will always check with the write counter, and then at the 0 0 0 your data D is written via data in to the entire bit. Okay, that D data can be C9. Let us consider an example. Now what we have done writing. So if we have D2, let us say it is D1. Now D2 is coming at the clock 1 another pulse. So at the another passage of the clock. So what happens? Again the counter increments and the counter incremented value is 0 0 1. So at that address location the counter value is given to the address location, and at this address location of the mem, see for mem, right, mem address location is 0 0 1. Just recollect how you have designed the previous things, and this memory 001 address location, the D2 will be sitting here. D2. That can be some other A3, that can be value like 10 10 0 0 1 1. So that is, this is A and this is 3. Okay, so like that some kind of data is stored in terms of 8-bit. Each one is 8-bit. So that data and now like this it has repeated for all the 8 registers, then your full logic will be 1. In the same way, let us understand how it is happening for the read process. So read process, now read enable is equal to 1, and at the read clock, the data, whatever the data is there in here, so read clock from the static memory, it is going to the read control. Read control will send a message to the read counter, so that after you have the full data in this particular location, for read counter, the last register will be the connected device here. And for the write counter, for writing process, always you need to take the first register, initial register. So it is at 0, it is at 7. So that is for read. So what are you doing now? After everything is full now, if there is no data, there will be no reading. If there is no data, no point of having a reading counter. But assume you have a read values here, and that read value comes to the comes from the, I mean that is already coming from the write counter. So every time you write, the write data will be sent in this downward fashion. But when you are reading, right, always reading will be happening at from the bottom to top. Reading, how the reading will happen? First consider the last register which has data and move towards the next bit and other next bit and next bit, because the address locations is decrementing. First it is 7, next it is 8, and next it is 6, and after 6 it is 5, 4, 3. In the read process it happens here, and then comes the output. So it will be going through the data out. Got it, guys? So that is how read counter address is generated. Now for the address, it is read counter. So to avoid the conflict, we always run with 2 different clocks. That is more feasible. And for the read, data output is more essential. For write, data input is most essential. Okay, let us go to the another analogy. Consider you have a registers in this floppy kind of thing in a circular notation at the pointer 0, at this location of 0, and you have 64 locations like this, 64 byte RAM, 64 byte RAM. Like for that 64 byte RAM, each register, 63 is a register, 62nd register, 61st register, each register has storage capacity of 8 bits. Okay, likewise all these are stacked up in a order. So 0 1 2 3. Just I have aligned this vertical fashion into a circular fashion. That's it. Don't get too much confused. In the circular fashion, why did I mention like that? Because at the initial position, address location will be 0. This is the address location, and we have a tail pointer and header pointer. Let us consider a condition at t is equal to h, then empty is equal to 1 and full is equal to 0. At t is equal to h, for example, both t and h will be at different points. I mean, at the initial stage, both will be at beginning points at the same point. At that same point, what are we indicating? Empty is equal to 1. Means there is no data in the entire stack of the memory. So what are we looking at? Empty is equal to 1 if they are both at the same location. But full is equal to 0. Why full is equal to 0? No data means full is equal to 0. No data means empty is equal to 1. Understand, in a normal layman technical terms, empty is equal to 1. For that, everything is empty. That's what the meaning is. Full is equal to 0. That means not full. Not full. If full is equal to 1, okay, it is full. That's what the meaning is. Understand? So when they are at same position, header location and header, sometimes it is represented with the write, and tail it is represented with read. So if they are both at the same initial point, then empty is equal to 1 and full is equal to 0. But if tail and header, tail pointer and header pointer are at different locations, then what it is considered as? It is considered as empty may be 1 and 0 or full may be 1 and 0. That means read and write process are done or it is going on. So we don't know. That we will get to know with the basic Verilog HDL understanding. Now let us write a single clock design FIFO. I'm just repeating again. Here is all. First in is Fi and first out is Fo. So in this way, the data decremented will be sent out. Okay, in this way data input is added here into the registers. Okay, so now let us consider the modules. What are the inputs we have? We have clock. With the clock we can also have reset, because to reset the entire design if it goes wrong, if it is abnormally working. And you can have buff input. Buff input is nothing but data input. And you can also have buff output. Buff output is nothing but data out. So write enable is this one, and you have read enable signal. So that read enable signal is this one. You have counter. That counter is this write counter or read counter, we don't know, but counter FIFO, it says about that thing. If counter FIFO is incrementing, then it is write, and if counter FIFO is decrementing, then it is read. Got it? Hence, understand there is only one counter. Why did I represent two blocks for this? Just to understand, just to make you understand this thing. But this in general, this is only one counter like this. This is only one counter, one static memory, and one RAM and one flag logic block. Okay, total we have 4 blocks only. Don't consider these as two separate counters. Don't get confused. I'm just explaining in a normal layman terms. Now flag empty and flag full. We should know the flag empty and flag full, right? That full and empty flags should be known. So did we consider all those? We have considered all those things with clock and write enable, read enable, data in, buff input, buff output, full and empty. Let us go to the code. You have declared the inputs. You have to declare outputs as well. Whatever you declare inputs, those can be wires, but here you have to declare registers, buff out, counter FIFO, flag empty and flag full, and also write pointer and read pointer. This declaration of two uh, declaration of pointer to the location of write and read task. Okay, and at last we have to mention the RAM, right? All these blocks, don't get confused, we are writing every block of the design. Hence you can also see at the always block. Now this always block will be focusing on status flags. Let us see what is flag empty and flag full. Okay, in this design we are coming from flag logic block. First always block. Okay, first always block is focusing on flag empty. When will be the flag empty? If counter FIFO is equal to 0 0. So in the starting point in the RAM, if the starting point is 0, then flag empty is equal to 1 and flag full is flag empty is 1. That means there is no data. And then if counter FIFO is at 64, okay, counter FIFO, now counter has been turned to the 64th bit, I mean 64th location. 60, if it is 0, it is 63 value. Then what is happening? If the counter is here, counter FIFO reaches 63rd value, then what happens? Flag full is 1. Understood? Remember this. Here when empty flag is 1, then the counter FIFO is equal to 0. That means when counter is 0, it is not allowed to read from the FIFO. If there is no data, if it is saying empty, what will you read? You can write into it, but you can't read from it. Big no. But write big yes. If it is empty. Empty is equal to 1. Vice versa. If flag full is equal to 1, if counter FIFO is equal to 64, then flag full is equal to 1. That means it is difficult to write into FIFO. Okay, now it is another condition. If your entire RAM is full, what will you write? There is no space for writing. Your EDA tool or any other thing will pop up saying, okay, this entire memory RAM is full. So it should say that full will be acknowledged only if counter FIFO reaches 64. Okay, at the time we can only write, we can only read from it, but we can't write. So that is the meaning, overall meaning of full and empty. So next, this always block will be working on the counter as per flag full or empty. Okay, now we are being more specific for the flag full and empty, when it should write and when it should read. Begin the condition. If reset in the beginning, if reset is enabled, if reset is 1, counter FIFO is equal to 0. Everything goes 0, right, when you reset any device or machine. Else if not flag full, one condition, and write enable. Okay, flag full is not 1, so it can be 0 or it can not be 1. Okay, then write enable, and flag empty is not okay, not flag empty, and read enable. In this point, both read and write task can be happening. So at the read enable and write enable, both are 1. Both are 1. Then you can see counter FIFO is equal to counter FIFO. It is at stable point. But else if flag full is not full, so full is not equal to 1 or not equal to 0, some in between the 0 and 1 transition, then write enable, you are writing the process, you have to write the enable. The initial condition is both read and write. Now you are writing, next you will read, that's it. By default counter FIFO will be counter FIFO. That's it for the flag empty and full represents. And flag empty is not okay, and read enable. So now it is not empty. Now it is not empty means you can read. If it is not full means okay, it is not full, you can write, you write it. It is not empty, there is something in it, read it. Simple explanations. Remember this what I have said. And for every write it increments, and read it decrements. Simple. Okay, for write it increments, and read it decrements. Now go to the next always block. This always block will be working on the data to fetch from FIFO, that is read. So now we are purely reading it. How do we read it? From the memory we will read it. So it is like begin the process, end it along. In between, if reset is equal to 1, where do we need to write the data? We need to read the data into buff out. So some from memory, consider this memory, and from that memory, from that memory location as well, you need to write into buff out. So that is what we are aiming for in the read. So now buff out is equal to 0. This reset is equal to 1 means the output is 0 when reset. Output is 0 when reset. Else, now begin. Now else means not reset. Reset is equal to 0. Begin. If read enable and not buff empty means the flag empty. That means when read underscore enable and empty is not 1, this can be flag, that is flag empty. And you can see read enable and empty is not 1, so FIFO is of data. So now it is not empty, some data is there. Then that data from the read pointer, like that read pointer is nothing but address location obtained from this read pointer. Now here it is read pointer is generated. From this read pointer is generated, that read pointer helps in locating from which data of the memory location can be obtained. Okay, that memory location data is sent through buff out. Else by default buff out is the same at all the conditions. Okay, begin with end, and this begin with end, and this end is considered in the later sessions. Now what else? For the read process is done. Now the write process has the same thing. You can write always begin and end, and begin and end in the if, and begin and end if write enable and not flag full, the entire RAM is not full. For that, write enable is equal to 1, the process is writing, and write enable is equal to 1, and flag full is not 1, flag full is not 1, or not flag full is nothing but okay, flag full is some other transition value 0 or 1. So memory pointer, so now it is 0, and memory write pointer to which location the memory should be written, that will be coming from buff input, like this one. So this is buff in. Okay, from that buff in it will go to the write pointer. So write pointer will be located, will be considered as the write counter, like a read pointer, write pointer. Okay, from that you can write the data into the memory. Got it? write the data into the memory. Else the write pointer with memory that stays stable. Okay, write pointer is head pointer and read pointer is tail pointer. Got it, guys? So in the last thing, always at the rate of passage of the clock or the passage of the reset, you have to reset the entire thing. For the first, both the write pointers and read pointers are 0 and 0, else begin not flag full, because now we have to take care of the pointers, right? We are using the pointers at different locations, but for that pointers we are mentioning address locations of the memory to read and write at different points. So for that, if not flag full, not flag full means you can write something on it, and write enable is 1. So write pointer is nothing but increment pointer. Okay, and else write pointer is same. If flag, if not flag empty, if not flag empty means empty can be 0. Empty can be 0 means there is some data on the memory and that read enable is there. So now read pointer plus 1 and read pointer. Read pointer is incremented in a downward fashion from the top. Hence you can see this read and write counter FIFO, all these things, and in a simple representation I have made from the EDA tools, you can see these things. And then tail pointer is always read enable data will be pushed from the buff out from the tail pointer, and head pointers write enable. Full and empty can be 0 or 1 logics. Okay, between one module and second module there will be some introduction to FIFO, writing out to FIFO and reading out from FIFO. So if you have FIFO, writing into FIFO, right, and reading out from FIFO. Done. So that is our class, and I hope you have enjoyed this entire session. And if you have any doubts and questions, please let me know. I'll answer them as soon as possible. And thank you for attending. See you.